One of the first things that we need to discuss in this class is vectors. So a vector is defined to be something that it is a quantity that has both a magnitude as well as a direction. Magnitude and direction. For instance, let's say that we have 30 miles per hour. 30 miles per hour gives us a magnitude. It tells us how fast we're moving, but it doesn't give us any direction. So this is a quantity we would actually call a scalar. A scalar does not have any direction associated with it. However, if we say we're going 30 miles per hour, let's say north, now we have a direction here. So 30 miles per hour north is a vector quantity. So this is a vector. Typically, we would note a vector. Let's say this is a velocity vector. This is actually the difference between velocity and speed is that velocity has a direction associated with it, so it is a vector. Speed does not have a direction associated with it, hence it's a scalar. So let's call this, we'll call this vector v. And the way we denote that it is a vector is that we put a line, or we put an arrow over the top, or a ray over the top, to denote that it has a magnitude as well as a direction. In your textbook, oftentimes it's a bold V that would indicate the fact that it's a vector, but when you're writing your notes and when I'm writing on the board, I'll typically just put an arrow over the top to indicate that it is a vector. So let's talk a little bit about vector notation here as well. So let's say we have a vector, and vectors describe where something moves, how far, and the direction it moves. Its location in space actually doesn't matter. We'll talk about this a little bit more here. So let's say we have a vector. We'll start at the origin, just for the sake of convenience here. We'll start out at the origin, and let's say it moves over 3 and x, so 1, 2, 3 in x, and 4 in y. 1, 2, 3, 4, and y. And so we have this vector that moves just like this, over 3 in x and up 4 in y. And so this vector, we'll call it vector A. We can denote it with this vector symbol, and there's a few ways that we can write. We can describe it mathematically. We can say that vector A is equal to, it's like an ordered pair, but we use this angled bracket instead here, and it moves 3 in x and 4 in y. And let's say, for the sake of convenience here, that this coordinate system is in meters. So we'll put the meters on the outside here. Okay, so vector A is 3 meters in x and 4 meters in y. Now it doesn't actually matter if it starts at the origin or where it starts. So let's say I start at another random place right here, and I were to move over 3 and up 4. Then this vector has the same magnitude and the same direction as the other vector, so this is also vector A. Vector A doesn't actually matter where it is in space, only matters where it is going. So that's vector A as well. Also, if I were to draw another one over here, let's say this one starts here, over 3, up 4. This is, again, vector A. A little bit of notation about the vectors, or a little, I guess, definition of the parts. This is what we call the head of the vector, where the arrow is, and where it starts, its origin, is called the tail. Okay? So vector A, if I place the tail at the origin, the head would be at 3, 4. Okay. There's a couple other ways we could write it. Most typically, I'll probably write it this way in class, but we can also write it in another form here. We could say that vector A is also equal to, write it like a matrix, or actually this is called a vector, 3, 4, in which this is the first one on the top is the x, and the second one down below is the y. If we had a three-dimensional vector, then we would have here, let's say that vector B was a three-dimensional vector. Maybe it would have the x and y components that the A does, and then let's just say it has some other z component as well. And we could also write it like this. Vector B would be 3, then 4, then some z component. However, in this course, we're not going to talk about any vectors in 3 dimensions. Everything we do will be in 2 dimensions. So some of the other really important parts of this vector is how it's moving in the x and how it's moving in the y. So in x here, it moves over 3. We can call this ax. So this is our x component of the vector A. So we'll call this ax. And this is its magnitude in x direction. We also have it moving in the y. This is ay right here. It's y component of the motion. Okay, so ax in this case is equal to 3 meters, the distance it moves in x, and ay is equal to 4 meters because it moves 4 meters in x. Okay, if I want to find the magnitude is how far it's gone. So it's really just, if we come back up here, the magnitude of a vector is really like this 30 miles per hour. That's the, I guess you could think of as the scalar portion of it. So the magnitude is just how far. It doesn't pay attention to the direction. And so if you look at this, then we have its magnitude is right here. And we can solve it knowing that x and y are perpendicular to each other, so we have a right triangle. So we can just use Pythagorean theorem to find its magnitude. So the magnitude of vector A, using Pythagorean theorem, and we denote magnitude with the absolute value. So that absolute value of A is the magnitude of A. And this is going to be the square root of the sum of the squares of its components. So this would be the x component squared plus the y component squared and the square root of this. Okay, so for vector A that we had above, the magnitude of vector A here is going to be equal to, the x component was 3, so this is 3 squared, plus the y component is 4 squared. This is equal to 5, or you might recognize this as a 3, 4, 5 triangle. So the magnitude of vector A is 5 meters. We can also figure out what the angle that it acts at, so we can describe it a little bit differently with the angle. So let me come back down here and redraw vector A. So vector A was moving over 3, up 4. So this was vector A. And let's say that we would like to we'd like to figure out what the angle is in standard position. So standard position is measured counterclockwise off the positive x-axis. So this angle we'll call theta. And then solving this, we know from our trig that tangent of theta is equal to the opposite over the adjacent. In this case, the opposite side is the y component. This is ay. And the adjacent side is equal to AX, the X component. So to find the angle in standard position, we can say tangent of theta is equal to AY over AX. And then we use the inverse tan function, so the arctan. So the arctangent of AY over AX is equal to theta. So for our 3, 4, 5 triangle here, we can find out what this the angle is. So we know that AY is 4, so the arctan of 4 over AX, which is 3, is equal to, plug in the center calculator, 53.13 degrees. This is the angle theta. So theta is equal to 53.13 degrees, which now we've found the angle in standard position, and we've also found the magnitude of vector A. So we can actually describe a vector. We don't have to describe it just the way we did up here, like this or like this. We can also describe it with a magnitude as well as an angle. And unless otherwise specified, that angle is assumed to be in standard position. So another way that we can write vector A, we have here vector A was 3, 4 meters, which can also be written as 3, 4. Put our units on the outside. And it's also equal to 5 meters, its magnitude, at 53.13 degrees. These are all ways in which we can write vector A. Another thing that I would like to take a look at in this video is what happens when you multiply a vector times a scalar. Let's say we have back here again vector A. So vector A, again moving, we'll start at the origin for simplicity again, moving 3 to the right in X and upwards 4 in Y. This is vector A. If I take vector B, and let's say that vector B is equal to 2 times vector A, then what this does is it scales its magnitude. It doesn't change its direction at all, it only scales its magnitude. And so writing A out, again, A is equal to 3, 4 meters. Then B, which is equal to 2 times A, is equal to 2 times 3, 4 meters. And we can just distribute this in and multiply it. This is how it moves here. So vector B is equal to 2 times 3 is 6, and 2 times 4 is 8 meters. So vector B would be 6, 8. So we would come over here, we would move 6, so that's 3, 4, 5, 6, and up 8, that's 4, 5, 6, 7, 8, and this would be vector B. And you see here, all it's done is we've taken and we've doubled the length of the vector. The length of a vector represents its magnitude, and then we draw the angle that it moves in. And so this is vector B. We can also multiply a vector by a negative, in which case, let's say again we have vector vector A that was 3, 4, and we wanted to find a new vector, vector C. And C happens to be negative of vector A. So this is going to be distributing a negative, and here it's going to be -3, -4 meters. So vector C would, if we start at the origin, actually we can start anywhere. Let's just start right here. And then we move. Negative would suggest that we're moving to the left and downwards. So in the x direction, we'll move 3 to the left, and then downwards 4, and we end up right here. So this is vector C, which is equal to negative of vector A. We call these vectors, they have the same magnitude. Vector A and vector C have the same magnitude. The magnitude of A is equal to the magnitude of C. However, C goes in the opposite direction of A, or A goes in the opposite direction of C. So we call these anti-parallel because C is equal to negative A. So this is anti-parallel to anti-parallel vectors. And that's some just definitions of vectors and how to write them.